The 1.154 multiplier, also known as 2/3 of the square root of 3, is employed to compensate for the increased current demand when a single-phase load is connected to a three-phase transformer. This phenomenon arises because the single-phase load exclusively utilizes 2 out of the transformer's 3 phases. To deliver the equivalent power as a three-phase load, the current draw on those 2 phases must be higher. Consider a 1 kilowatt single-phase load operating at 208 volts. This load would necessitate approximately 4.6 amps. Conversely, a 1 kilowatt three-phase load at 208 volts would only draw about 2.7 amps. This illustrates that the single-phase load demands approximately 70% more current compared to its three-phase counterpart for the same power output. The 1.154 multiplier effectively accounts for this disparity in current draw. Mathematically, it's derived as the square root of 3 divided by 2, representing the ratio of current drawn by a single-phase load relative to a three-phase load. When determining the cumulative load on a three-phase transformer, it is crucial to apply the 1.154 multiplier to the wattage of any single-phase loads. This adjustment ensures that the calculation reflects the higher current they will draw compared to three-phase loads. In your provided scenario, an 8-amp motor load connected to a three-phase transformer would present a load of approximately 1920 volt amps. This is because the motor draws roughly 70% more current than a comparable three-phase load. Let's delve deeper into why this current difference is significant and how it impacts transformer loading. When a balanced three-phase load is connected to a three-phase transformer, the current is evenly distributed across all 3 phases. This balanced loading optimizes the transformer's capacity and efficiency. However, introducing a single-phase load disrupts this balance. The single-phase load draws current from only 2 phases, creating an imbalance in the current distribution within the transformer windings. This imbalance has several consequences. Firstly, it can lead to increased heating in the phases supplying the single-phase load. The higher current in these phases generates more heat due to the resistive losses in the windings, described by the I/R relationship. Excessive heat can degrade the transformer's insulation and reduce its lifespan. Secondly, the unbalanced current can cause voltage imbalances on the three-phase system. The voltage drop on the phases supplying the single-phase load will be greater than the voltage drop on the remaining phase. This voltage imbalance can negatively affect the performance of other three-phase equipment connected to the same transformer. To mitigate these issues, it's crucial to accurately account for the impact of single-phase loads on three-phase transformers. The 1.154 multiplier provides a simple and effective way to do this. By multiplying the single-phase load wattage by 1.154, engineers can estimate the equivalent three-phase load that the transformer will experience. This allows for proper transformer sizing and protection to ensure reliable and efficient operation. Furthermore, the use of the 1.154 multiplier is consistent with established electrical engineering practices and standards. It is recognized by organizations such as the Institute of Electrical and Electronics Engineers and is often incorporated into electrical design software and calculations. Now, let's consider some practical examples of how to apply the 1.154 multiplier in real-world scenarios. Imagine a small commercial building supplied by a 480 volts to 208/120 volts three-phase transformer. The building has several three-phase loads, such as HVAC equipment and pumps, as well as some single-phase loads, like lighting and receptacle circuits. To determine the total load on the transformer, the engineer would first calculate the volt-amps for each three-phase load. This is typically done by multiplying the voltage, current, and the square root of 3. Next, the engineer would calculate the volt-amps for each single-phase load. However, instead of simply multiplying the voltage and current, the engineer would multiply the result by 1.154. This adjustment ensures that the single-phase loads are properly accounted for in the total load calculation. Finally, the engineer would sum up all the volt-amps for both the three-phase and single-phase loads to determine the total load on the transformer. This total load is then used to select a transformer with sufficient capacity to handle the building's electrical demand. In another example, consider a manufacturing facility with a large three-phase motor and several single-phase welding machines. The welding machines represent a significant single-phase load that must be carefully considered. Again, the 1.154 multiplier is used to adjust the volt-ampere rating of each single-phase welder. The NEC, or National Electrical Code, provides guidance on transformer loading and protection. Although it doesn't explicitly mention the 1.154 multiplier, it does emphasize the importance of accurately calculating the total load on a transformer, including both three-phase and single-phase loads. The NEC also specifies requirements for overcurrent protection to protect the transformer from overload and short circuits. These protection devices, such as fuses and circuit breakers, must be sized based on the transformer's capacity and the expected load. In addition to the 1.154 multiplier, there are other factors to consider when dealing with single-phase loads on three-phase transformers. One important factor is load balancing. Whenever possible, single-phase loads should be distributed as evenly as possible across the three phases of the transformer. This helps to minimize current imbalances and voltage imbalances. Load balancing can be achieved by carefully planning the wiring of the single-phase circuits and by using phase rotation to alternate the phases to which the single-phase loads are connected. Another factor to consider is the transformer's impedance. The impedance of a transformer affects the voltage regulation and the fault current. Transformers with lower impedance will have better voltage regulation but will also have higher fault currents. Conversely, transformers with higher impedance will have poorer voltage regulation but will have lower fault currents. The choice of transformer impedance depends on the specific application and the requirements for voltage regulation and fault current. Furthermore, it's crucial to understand the different types of three-phase transformer connections. The most common types are delta and Y connections. In a delta connection, the three phases are connected in a closed loop forming a triangle. In a Y connection, the three phases are connected to a common neutral point forming a star shape. The choice of transformer connection depends on the voltage levels and the grounding requirements of the system. Delta Y transformers are commonly used to step down voltage from a high voltage transmission system to a low voltage distribution system. YY transformers are often used in applications where a neutral conductor is required. Understanding these concepts is essential for any electrical engineer or technician working with three-phase power systems. The 1.154 multiplier is just one piece of the puzzle, but it is a crucial piece for ensuring accurate load calculations and reliable transformer operation. Ignoring the impact of single-phase loads can lead to undersized transformers, overloaded circuits, and potentially dangerous situations. Therefore, it is always best to err on the side of caution and apply the 1.154 multiplier whenever single-phase loads are present on a three-phase system. By doing so, you can ensure that your electrical system is safe, efficient, and reliable. It is essential to remember that electrical codes and standards may vary depending on your location. Always consult the relevant codes and standards for your specific jurisdiction to ensure compliance. Additionally, it is recommended to seek the advice of a qualified electrical engineer for complex electrical design projects. Proper planning and execution are critical for ensuring the safety and reliability of electrical systems. By following best practices and adhering to applicable codes and standards, you can minimize the risk of electrical hazards and ensure the long-term performance of your electrical infrastructure. The application of the 1.154 multiplier is a testament to the importance of understanding the nuances of three-phase power systems and the impact of different types of loads. It highlights the need for careful analysis and precise calculations to ensure the safe and efficient operation of electrical equipment. In summary, the 1.154 multiplier is used to correct for the higher current draw of single-phase loads when connected to a three-phase transformer. It's derived from the square root of 3 divided by 2, which represents the current ratio between single-phase and three-phase loads. This multiplier is essential for accurate load calculations, proper transformer sizing, and ensuring the safety and reliability of electrical systems. Remember to always consider load balancing, transformer impedance, and the type of transformer connection when working with three-phase power systems. And finally, consult with qualified professionals and adhere to applicable codes and standards for all electrical design and installation projects.